Welcome to session 4 of the Amateur Radio Technician Online Licensing class. We're going to start today's lecture with modulation. And let's start by looking at the technician license allocations, which are part of the band plan. And we'll get into more detail about the band plans a little later in the lecture. However, I want to focus here first to give you some idea of why we're going to be as broad as we're going to be in the lecture, because most people think of the technicians working mostly VHF, UHF and above, doing mostly FM voice, and that's not the case. There's a lot more available to the technician than that. And so you have allocations in the HF band, and mostly these are Morse code and data allocations in the 80, 40, 15, and 10 meter band. But you also have a voice allocation in the 10 meter band, 28.3 to 28.5 megahertz. And this is important because that's where there's a lot of SSB or voice activity. And especially right now during solar cycle 25, when we're at peak, we are able to use that band and effectively communicate around the world. So it's not unusual to be in Seattle and talk to someone in Barcelona or in England or even into South America on voice with 100 watts or 50 watts or 20 watts even, depending on ionospheric conditions. And so this is really a nice space to, as a technician, to sort of flex your muscle, so to speak, or get some experience in using voice and even doing the 10 meter contests. And then you have allocations, of course, in the 6 meter, 2 meter, the 1.25 meter VHF bands. And then, of course, UHF and above, as we've talked about before. And when we say above, we're really talking really high. So technicians have the same allocations as everybody else in these higher bands, in the UHF bands and higher. So you can see you also have allocations in the 2.4 gigahertz or 2300 to 2400 megahertz bands. You have allocations in the 5 gigahertz bands and 10 gigahertz bands. And I point those out because that's where a lot of internet work can be done in those bands. They're very similar, close to consumer Wi-Fi bands. So there's a lot of work that being done there. As well as you can see, we go anything above 275 gigahertz is open field for anyone to do any experimentation that they'd like. So there's a lot of opportunity here for exploring the hobby in the technician realm. So given this, let's talk about now how information is transported on a radio frequency wave. So first, let's do a little quick review. Audio frequencies are about 20 hertz to 20,000 hertz. They can't radiate through space. Now, if there are people who have been educated back in the, prior to 1980 or so, they'll probably use a different allocation for audio, not allocation, they'll probably use a different designation for audio frequencies of 16 hertz to 20,000 hertz. It's just recently that I noticed that the Amateur Radio licensing manual has changed that to 20 hertz. I was educated back in the 70s as this being 16 hertz. So either way, you can see that the upper band is 20,000 hertz for audio frequencies, and they cannot radiate. They do not have enough energy to radiate through space through the transfer of energy. Radio frequencies above 20,000 hertz, and again, when I was being educated back in the 70s, we considered radio frequencies starting at 40,000 hertz, but the book is now listing as 20,000 hertz. They're able to radiate. There's enough energy that they can radiate through space without any medium. And that's the difference between audio frequencies and radio frequencies. Audio frequencies cannot go through space without being transported by a medium like air or water. Radio frequencies can transmit through space through a vacuum. They don't need any type of medium to make them move or to get them from point A to point B. They have sufficient energy, and that's why we call them a carrier frequency. And you'll hear me refer to intelligence, or other people refer to intelligence, and that's the information carried by radio frequencies. So as you can see on the right, the RF wave can be simply just turned on and off to represent a minimum of 2 states. We have an on state and off state. It's a digital state, right? You have on and off, 1 or 0, and you can just turn the transmitter on, turn it off, turn it on, turn it off, and that will indicate intelligence. It's going to be a low level of intelligence. That is, we don't have a lot of complexity that we can show there, but it is intelligence that can be transported from point A to point B. Now, We can also have other modes of transport, and here we have RF being turned on and off for specific periods of time to represent more than two states. So this is an example of Morse code where we have da off and dit off, da off. So you can see that we can now create not only on and off, but we can also create states where there's a specific time that it's on and a specific time that it's off and a specific time that it's back on again that are different intervals that can carry additional intelligence. So now, for example, we can use da, dit, da to represent a K, or dit, 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 da to represent a V. So we have more complexity or more intelligence that we can send by just simply turning on and off the carrier wave. And this is a very simple way of transforming or transmitting information from point A to point B. So we just described basically is how a transmitter works, and we can look at this, and again, any audio frequencies greater than 40,000 kilohertz. Again, I forgot to change that from my last time I gave the lecture. It should be 20,000 kilohertz, sorry. And we need a way to turn off and turn on the carrier. Could be as simple as a switch, which is essentially what a Morse code key is. It's just a form of switch. This has got a small bandwidth because it's got a very limited amount of information it can carry. It has a high power density though, which means that simply turning it on or off very quickly, you can put 100 watts into a very small pulse and it will actually travel further than the same 100 watts that's delivered over many, many different frequencies that it has to reproduce. And we'll get into that a little more later so it makes more sense. But when we're just turning it on and off, just keep in mind that the information density is low per unit of time. And so if we look at this, we have a fixed oscillator, which is we have an inductor and a capacitor acting as a resonance circuit that's fixing the frequency of oscillation for this oscillator. That oscillator is producing a radio frequency. It's up at greater than 20,000 hertz. It's going into a driver amplifier and then a power amplifier to boost it up to enough energy that it can travel beyond just a few feet, but can go further and further than that. And so we use a switch to, in the simplest form, is to turn the amplifiers on or off. And so when they turn the amplifiers on and off, we have information. And that's very simple. It's very illustrative. This is not the details of how the circuit actually works. It would be inefficient to turn the power supplies on and off like that. There are other ways of doing it that are more effective and more efficient, but you get the idea that all we're doing is turning the carrier wave on and turning the carrier wave off. We're setting at least on certain intervals that could be used to represent, for example, Morse code, dits and das. Now, when we deal with frequencies above 50 megahertz, you'll often hear CW, continuous wave, otherwise known as Morse code, referred to as a weak signal mode. Below 50 megahertz, you won't see that used as a common term because those are normal signals like SSB and CW, which are called weak signals. Above 50 megahertz are generally just common signals below 50 megahertz, so we don't usually refer to as weak signals. But you will hear that term, that they're weak signals. Specifically, we're talking about VHF and above. So we have the same basic circuit here, but by adding a variable capacitor or a variable inductor, we can now change the resonant frequency of that tank circuit, which is setting the frequency of the RF carrier to that oscillator, and that's being amplified, which means instead of just being able, in the previous example, to transmit only at one frequency, now we can adjust the variable capacitor or the variable inductor to change the rate of oscillation, which allows us to transmit at different frequencies. And that's simply, this again, a very simple illustration of how a transmitter using continuous wave or Morse code works. So moving away from Morse code to moving into some more complex signals, we have to do some audio frequency transducing, or to use audio frequency transducers. And the idea of transducers, that meaning of that word is really to convert one form of energy into another form of energy. So for a microphone, when we're talking into a microphone, which means we're vibrating we're vibrating air molecules that are hitting some surface, the transducer is used to convert the changes in the air pressure from my voice or music, a vibration, to an equivalent electrical equivalent electrical signal. And we have two different types of microphones. Again, this is just for your information. We have a dynamic microphone, which is the top one, and we have a condenser microphone, which is the lower illustration. Now, you remember that when you move a coil through a magnetic field, you produce a signal, an alternating current signal. So if you attach the diaphragm of the microphone, the section of the microphone where voice or air molecules are going to be hitting, and it starts that diaphragm moving, then since it's attached to the coil, it will move in and out of the magnet, which produces a electric signal that can be used and amplified by the radio or other device. We have a very similar function below where we have two metallic plates, the diaphragm being one of those metallic plates. Again, sound is hitting that diaphragm. It's changing the distance between those plates. Well, remember, when we have two metal plates that are separated by some sort of insulator, in this case air, it's a capacitor. And so by applying a small electrical signal, DC signal, to the plates of this capacitor, and the capacitor is changing its distance between its plates, this will change the charge on the capacitor, and that charge will represent the lower audio frequency signal that will now be amplified by the radio. And there are advantages and disadvantages for both types of approaches. In amateur radio, you'll see many of them are more dynamic microphones than they are condenser microphones. Again, for most people, this is a level of detail you don't necessarily need for the test, but it's just some information that might be helpful for you in broadening your scope of the hobby. On the other side, we need a speaker, and a speaker is a transducer used to convert an audio frequency wave to changes in air pressure, so we can then do the reverse. If we have an electrical signal that's varying in frequency based on voice, for example, it's a low frequency, it doesn't radiate, and then we cannot hear electrical signals. If I threw electrical signal out in some way through, again, an antenna, I can't hear that. My brain is not set up to deal with that. My senses are not set up to deal with that. So we have to have some way of converting that electrical signal that represents the voice into mechanical movement in the air. And so that's what a speaker does. And we see the coil once again in a magnet, surrounded by a magnet. And as we put the signal through that coil, it's going to interact with the magnet, and it's going to move the speaker's cone, and that movement will then cause the air molecules to be moved, and therefore we'll be able to create an electrical signal being converted to a mechanical motion in the air, which our ears are designed to pick up. And so that's how we move sound. We can take vibration from the air and convert it to a signal, and we can take the signal and convert it to a vibration in the air. And if you notice carefully, the dynamic microphone and the speaker are very, very similar. In fact, you can actually take a speaker and use it as a microphone, and vice versa. They won't be great, but they will work in that way if they're both in this kind of design. So let's go back to how information is transported on an RF wave. What about moving lower non-radiating audio frequencies like voice, data, or music? Now, voice is a complex waveform. It's a composite signal with component frequencies spanning 300 to 3000 hertz. That's a bandwidth of 2700 hertz, or 3000 minus 300. So that's how much bandwidth, that's how much space, that's how wide the frequency span is going to be if it's going to be reproduced with enough fidelity for people to hear it clearly. Music, on the other hand, is also a complex wave, but it runs from 20 to 20,000 hertz, which is a bandwidth of about 20,000 hertz. So if you were to reproduce the music with only a bandwidth of 2700 hertz like voice, you would not get a nice, warm sounding piece of music on the other end. It would be sounding very cut off, very changed, because there's not enough bandwidth to reproduce that sound. But if you were able to use the full 20,000 hertz for bandwidth, then you would get rich sound, often like FM or stereo AM, a much more richer sound because you have all the bandwidth available to reproduce the sound. So then to transport the low frequency audio frequency intelligence that can't radiate, we need to superimpose it onto an RF carrier. Or to put it very simply, we're going to put a snail on top of an eagle, and the eagle is going to get that snail from point A to point B. And we call that process of superimposing the lower frequency intelligence onto the carrier wave modulation. So what is modulation and then demodulation? Modulation is transmitting. We put the snail on the eagle and we give them a push, and they go off to some distant location where they're received, and there at the receiving station we stop the eagle, we remove the snail, and now we have the audio frequency that we need to do something with that was transported where we couldn't have done that before. So modulation, we superimpose the AF onto the RF. Demodulation, remove the AF from the RF, and then we can utilize the AF to power an amplifier to go to a speaker, for example. So let's go back to our simple idea of a transmitter again, and by adding a modulator, a specialized circuit called a modulator, it allows a low power, as I said, or lower frequency signal containing more information to be combined with a higher power RF signal. And the RF signal carries the information from, as I said before, from the transmitter to the receiver. So here we have a simple circuit illustration. We have our variable oscillator, so we can adjust what frequency we're going to transmit at. It's at a radio frequency that's greater than 20,000 hertz. And then we have our microphone picking up a voice frequency, which is going to be between 300 and 3,000 hertz. In this case, we're just stating its voice. It's going to be amplified, and then we're going to superimpose that audio frequency signal onto the RF signal. And you can see the resulting waveform, and if you look at the resulting waveform, you can see the outer perimeter of that resulting waveform is a mirror image, or not a mirror, it's an actual image of the audio amplifier signal coming in. And then that's going to be amplified further so it has sufficient energy to travel far enough to be able to be heard by many stations in a further location. When we are adjusting the amplitude of the carrier wave to correspond to the intelligence, we call that amplitude modulation, also known as AM, and you've probably hear it as the AM band. So the AM band, which is a medium frequency band, it utilizes amplitude modulation. And this is essentially what it's doing. So again, looking at amplitude modulation, we can see that we have the red carrier wave, we have the yellow, or can be the green input or lower frequency audio, and then we are going to superimpose them. We're going to adjust the carrier wave to match the amplitude changes in the lower frequency audio, lower frequency intelligence to get a waveform out that will have enough energy to travel through space. When we do this idea of modulation, when the circuit that does the modulation is working, what we get is the carrier wave, the original wave, and then we get two sidebands, a lower sideband and an upper sideband. The carrier wave itself carries no information. Now remember, the carrier wave has been altered by the low frequency audio, and that's in the lower sidebands. But when we do this mathematically, which is what electronics is all mathematics, we not only get the lower sideband, the upper sideband, but we automatically get a non-intelligent carrier wave, and that comes along for the ride. And so that's what an AM modulated waveform would look like on a spectroscope, basically. And the transmitted power is distributed across the entire bandwidth of signals. So if I have 100 watts that I'm transmitting at, then that 100 watts is distributed across the lower sideband, the carrier, and the upper sideband. That will be the entire power is going to be dispersed across all of that space, all of that bandwidth. So again, single sideband, like I mentioned before, is one type of weak signal work, and it's got less fidelity and higher power density than amplitude modulation. So single sideband has less fidelity. If you're trying to reproduce very rich voice, for example, it's not going to be as rich as if it had the other sideband with it, but it's good enough. And because, and you'll see in a second, it's because of the way it's designed, it's going to have a higher power density than AM. Let's look at that. On the top left, we have the original AM modulated wave. We're going to run it through a special thing called a filter. And that filter is going to remove that non-intelligent carrier wave. There's no need to pass that carrier wave, because it carries no intelligence, into the final amplifier and put energy into boosting it even further. There's no need to do that. So we're going to suppress the carrier. And then we have a choice. Because the left side and the right side are basically images of the same information, we don't necessarily need both of them to be able to get enough information out of the waveform. So we can filter out the higher sideband, or we can filter out the lower sideband. So let's assume we're going to filter out the lower sideband. So we're going to go through the high pass filter, which means only things that will be higher than the low pass filter in frequencies will pass. And so we're only left with the high, the USB, the upper sideband. Now think about that. The, the space that that upper sideband takes is much less, and let's essentially say half, of what the full AM signal had before, which means now that 100 watts is being distributed through a smaller amount of bandwidth, which gives the signal more range, because instead of being average power being less than 100, it's going to be higher than it was before, because we've distributed the energy over a smaller space. The same with the low pass filter. Since we got rid of the other half, the upper sideband, and we've put 100 watts into only one half the signal, we're going to have a higher power density. So let me just say that one more time. If we look at the full AM wave without the carrier, and we're going to pump that up to 100 watts, we have to distribute 100 watts across both of those humps. But both those humps carry basically the same intelligence. But so we don't need both humps, especially for voice. So therefore, we just filter out that one of those humps, and we put all of our amplification into the remaining hump, which means that we're going to put 100 watts instead of being across 2x, being two humps, we're going to put it across 1x or one hump. And that means we're going to have a higher power density, which means the signal will go further. And generally, in single sideband operation, any frequency below 10 megahertz is considered lower sideband by convention. That is, we're all going to set our receivers and transmitters to handle lower sideband. Above 10 megahertz, we're going to set our receivers and transmitters to only utilize the upper sideband. And that way, by convention, we don't have to guess which one is which when somebody is transmitting or you want to receive it, or vice versa. There are some exceptions to this. On the 16 meter band, everything is upper sideband. And for digital is always upper sideband. And those are the only exceptions. So if you were going to want to talk to somebody on 40 meters, which is going to be 7.2, let's say, megahertz, then you know that's below 10. So by convention, we're all going to use lower sideband. If we're going to talk to somebody who's at 28.3 megahertz, the 10 meter band, we know by convention that we're both going to set for upper sideband. There are, of course, other other modulation types. We have amplitude modulation, what we just discussed. We're changing the amplitude of the carrier wave with respect to the lower frequency intelligence. Now, amplitude modulation is susceptible to man-made and natural RF noise, like thunderstorms or lightning. So whenever you have lightning strike, you will see the amplitude of an amplitude modulated wave change as another waveform is superimposed onto it. And because the radio is looking for an amplitude modulated wave, then you will be able to hear static crashes on AM. You'll hear certain types of man-made noise, RF noise, on AM because the radio is optimized to listen to changes in amplitude, and that's where man-made and also natural RF noise generally occur in the amplitude changes. Frequency modulation, we are going to take the low frequency intelligence and we're going to use it to adjust the range of frequency deviation or changes in frequency from the carrier wave. So for lower frequencies, we're going to lower the carrier wave, and for higher frequencies, we'll increase the carrier wave within a certain bandwidth. And so by changing the frequency to high and low and anything in between the two ends of that spectrum that we've defined for that channel or for that band, then we will be able to reproduce sound. And so that's how we do it. And we have circuits that do the demodulation of frequency, which is very different than demodulating amplitude modulation or single sideband. There's also a special effect called the FM capture effect, where only the strongest signal will be heard. So if you have two signals coming into an FM receiver, the one that's stronger will be the one that will be captured and be amplified. The other one will be generally ignored. We also have other forms of modulation like pulse modulation and phase modulation. And we're not going to get into any detail on those right now. So I've been alluding to this idea of power being spread over the used bandwidth. And to give you an example, this is from the book. This is a table of the bandwidth of different types of modes, or also known as emissions types. When we talk about modes, we're also going to talk about emissions types. CW Morse code has a bandwidth of 150 hertz. Single sideband digital can range from 500 hertz to 3000 hertz. And SSB voice from 2 to 3000 hertz, and FM voice from 10 to 15 kilohertz. And you can see commercial video and FM broadcasts have a wider bandwidth. Why? Because they have to reproduce more frequencies to get better fidelity and better reproduction. But what does this mean when I talk about power spread over the bandwidth? So this is not the actual calculation. This is just to give you an illustration, to give you an idea of what's changing as we talk about bandwidth. Let's assume we have a 50-watt transmitter, and let's just assume these are an illustration of the bandwidth of power density. If we look at 50 watts divided by a CW bandwidth of 150 hertz, we get a ratio of 0.33. If we divide that 50 watts across 2,800 hertz for an SSB voice, we get a ratio of 0.02. So if I wanted the voice to go as far as the Morse code, I would literally have to raise the energy level by somewhere over 10 times to get the equivalent range in power or equivalent power density to CW. Again, these are not the actual numbers, it's just illustration to show you as I spread the power, the number of watts I'm going to send out of the antenna, across a wider bandwidth, the average power across that is going to be lower. And that's why to get the equivalency as the bandwidth shrinks, I'm putting more power per unit bandwidth into that signal. This just gives you an idea of what it's like. And that's why when people tend to want to do Morse code, and they're able to go very far in Morse code with 5 watts or 10 watts, and you're barely making 800 miles with an SSB signal at 100 watts, oftentimes it's because they have a higher power density. And for digital data, we have other types of modulation techniques. We can use FM, of course, to do something called packet radio, which is, if you think about the old computer modems, that's very much what it was like. We have what's called audio shift keying, where we use 2 audio frequencies to represent on and off respectively to send digital data. We have frequency shift keying, which is we're very much like ASK, but we're using carrier frequency changes. And then we have phase shift keying, which is how we start and stop a waveform, can imply a 1 or a 0 or some type of intelligence in the wave. And each have a special circuit for demodulating these. Now, one of the things that you have to keep in mind when you're operating in HF modes and some other modes or weak signal modes like SSB is what the waveform is going to be like. So here we see a 20-meter band. That is the 14 point. This is where we are 14.3 megahertz. That area is in the 20-meter band. It's in our allocation. And let's say 14.35, by the way, is the upper end of that band. Now, by convention, we know that at 20 meters means that we always use upper sideband for voice communications. So if we remember that that signal is about 3 kilohertz, so that the signal is going to go from 14.35 kilohertz to 14.353 kilohertz. But our allocation is only up to 14.350, which means you're operating illegally. So you want to be very aware of the kind of signal you're using, what mode you're in, and that bandwidth to make sure that you don't operate over your allocation or outside your allocation. Conversely, if I was in the 7-meter band, which is going to be lower sideband, and the lowest frequency that we have allocated for in the 40-meter band or the 7 megahertz area is 7 megahertz. And so if I put my radio to 7 megahertz, I'm using lower sideband, which means my bandwidth is going to be below 7 megahertz and I'll be operating illegally. So you want to make sure you're not operating near the band edges so that you potentially could drift into an area where you don't have a legal allocation. So just be cognizant of that. We also have things called overmodulation that can happen. Excessive modulation of a SSB digital and AM signals can cause splatter, which interferes with others. That means it spreads your bandwidth across a wider area, which is what you're not allowed to do. If your voice, you're supposed to stay at 3,000 or less. If you're sputtering because you're overmodulating, you're going to beyond that, and you're going to interfere with other stations potentially. And oftentimes, SSB name overmodulation is caused by speaking too loudly, having a mic gain that's too high, or having a high voice compression. And so we won't get into details about what voice compression is, but just to know that there is something called voice compression. Essentially is a way of reducing the bandwidth of the voice signal, maintaining intelligence but putting more energy into less bandwidth. If that's up too high, you can have overmodulation. With FM, overmodulation causes excessive deviation, and deviation or overdeviation means that if you're supposed to only have a bandwidth of, let's say, I'm going to arbitrarily make this up, from 28 megahertz to 28.2 megahertz, and you're speaking so loudly, your FM signal is going to 28.22 megahertz, which is over what I just said, which is 14 or 28.2. That's over deviation. That's generally due to speaking too loudly, and you'll often hear the other amateur radio operator, say to you, "Hey, you're a bit distorted. You're overmodulating. You might want to either do one or two things: move the microphone further away from your mouth, speak at a lower volume, or if you have mic gain turned on, turn your mic gain down a little bit." So let's look at some examples of single mode and all mode transceivers. Single mode transceivers are basically ones that do only one mode, in this case FM. So we're talking mostly only here about FM as a single mode. And when we do FM, we can also do data. So oftentimes we can do data with FM as well. So even though I'm using FM here as the single mode, it is possible to do some types of data modes with FM as well. So we have on the top left a dual band FM, VHF, UHF mobile radio. This is a true dual band radio, which means it has two separate receivers. So they're dedicated. So it's not one receiver being shared by different parts of the radio. It is two separate receivers. It's actually more expensive that way, but it has some very significant advantages to do that. Below that is a Bofang dual band FM handy-talkie. This also has the ability to do two channels and to hear two channels at the same time. You can only transmit on one channel at any given time for either of those two radios. The difference is that the Bofang HT is not a true dual band radio because it has one receiver and it's just switching very quickly between the two rather than having two dedicated receivers. And then we have a 10-meter FM mobile unit. And then we start moving into all mode units. So multimodal units are going to be things that can handle SSB, AM, FM, CW, and data. So the one in the top center, all mode 2 meters, 7 centimeter, 1.25 gigahertz, this radio is optimized, of course, to operate in SSB, CW, data, and FM. But more particularly, it's also designed to work with satellites because it has a lot of capabilities for programming in and moving across the spectrum for Doppler shifts when dealing with satellite communications. So this one's been optimized for satellites. One of the things you can tell is that there's often a 2-meter uplink, and that should be 70 centimeters, not 7 centimeters. It should be 70 centimeters. I apologize. And there's often a downlink of 70 centimeters, or you can have a downlink of 1.25 gigahertz. You can have an uplink of 70 centimeters. Again, that was a typo there. I forgot to put it in. So this radio is optimized for all mode, but additionally, it also has functions and features to support satellite communications. To the far right, we have a high-frequency multi-mode HF radio. This is a Xiegu G90, very popular radio. Has a built-in antenna tuner. It runs 160 meters to 10 meters in span, and it runs 20 watts output. And you can see that it has a lot of information on the little grids there, on the little screen. Then we have the FT991A, which is one of my radios. By the way, the G90 is also a radio I own. And it's what was called the Shack in the Box because it does not only HF, it also does VHF and UHF. It's all mode. So you can operate repeaters from that as well as do SSB. And then we have an ICOM 7300 below that, which is also an HF multi-mode to 160 meters, 10 meters, and 6 meters. So let's talk some about radio functions. On these radios, you enter the frequency through the keypad or some sort of knob. On the top left, the FT8800, you have a knob on either side for each one of the receivers that you can turn to change the frequency of the radio or that receiver on that side. And in software, you can change the step rate for that. As well as on the right side with the HF radios, you have knobs that allow you to step through different tuning rates. One at the top of the G90, you push the tuning knob and you can scroll through what digit you want to start changing on. In the lower one, the FT991A, the rate at which you turn the dial determines how fast you'll go through the frequencies. So if you want to go very slow, then you just turn the dial slow. If you want to go faster through the band, you can just move the tuning knob faster. And of course, all these pretty much have microphones that have keypads on them for doing direct entry of a frequency into the radio through the keypad, plus accessing other features. Now, every radio has a power control, and it's just a matter of looking out to where it is. And the key to think about modern radios is that they use software menus to control many of the radio's parameters like squelch and tuning step, power levels, microphone gain, as well as setting up the repeater operation is all done in software. In fact, when you look at a modern radio, you see all the switches on the outside, and there are two types of switches: soft switches, like that are on the touch screen or the screen here, and on the right side you see what look like hardware switches, which they are hardware switches, but they're actually being defined and listened to through the software, through the computer. So those switches, when you push the button, it's not like what you're doing is accessing a part of the software program to make the change. And so that's almost all the features of a radio today are all in software. Even though you may be pushing a button, it's really the software doing all the work. And so again, power is often set by a software menu and using a rotator knob. And so if you look from the lower left, we have a soft switch. It's called RF output power. That's defined in the software. I've actually, in this model, you can set what switches you want to be soft switches. So I often need to look at different meter readings. I need to be able to adjust my power, maybe adjust my mic gain. So I have them set up as soft switches on my screen so I can use them very quickly versus having to go through a menu structure and find them. So we have RF power. I can push that button, and I can then rotate what's called the multi-knob, which is in the center lower of this device, and that will then adjust the power level. I can then push the mic gain, and I can use that multi-button now to adjust the mic gain. And there's also another button for mode, which is going to be saying SSB, FM, CW, or digital, or upper sideband as well as lower sideband SSB. What band am I going to be into by pushing the band button? We have a way to activate our memories and deactivate memories. So by hitting V, I am now no longer in memory mode. When I'm activating the M, I'm in memory mode and I can access all my memories of where I stored my frequencies and other information. We also have an AF gain button on the far right, and sometimes you'll see the AF gain and RF gain buttons will be two buttons, one inside the other, on top of each other, and so you adjust them, either the outside ring or the inside ring, to just one or the other. But in this case, they're separate buttons. AF gain, or audio frequency gain, is your traditional volume button. RF gain is like the volume control for the RF amplification, and so if I turn up the RF amplification, I will hear weaker signals. And if I turn it down, I will not hear as many weaker signals. However, you have to keep in mind is when you turn up the RF gain, you not only are amplifying the signal that you're trying to hear, but you're also amplifying the noise that the signal is within. So you're amplifying both the signal and the noise when you turn up the RF gain. And you can see the bigger knob in the center is the tuning knob that we use. And we also have a place for a Morse code key. And then on the right you see two different types of Morse code keys. And one is what's called a straight key, the one on the top, and the one on the bottom is called a vibroplex or bug. And they have two knobs. One knob you push and it forms a perfect dit, and the other knob you push and it forms a perfect da. And you get used to using, moving your two fingers to send the Morse code with that versus pushing up and down on the original straight key. And CW, Morse code, is still used by many. And in fact, there's been a really big resurgence of people using Morse code today. So the ranks of people using Morse code is going up. And again, especially when the ionosphere is not doing so well, like in the previous solar cycle where ranges were limited, going to Morse code gave you a little bit more ability to make contacts than just using voice alone. Now, computers are getting better at reading Morse code, but they're still not as accurate as a human. And that will probably change with time, but there's a lot of things that one has to understand when the computer is trying to read Morse code, or anyone's trying to read Morse code, but more quite accurately, precisely the computers have to deal with, which is not only having to pull the signal out of the noise so that one can figure out, is that, can I differentiate that dit and da against the noise of the RF, naturally made RF, and the other is that it's being sent by humans. And because it's being sent by humans, everyone's slightly different in their timing. And therefore, the computer has to actually figure out for each person sending what their unique timing is when they're sending a dit and da and their rate of off time or space time. That is the time between digits that they're sending or words. And that's not uniform because it's humans, and then the humans are not uniform. In fact, this is so well known that going back over 100 years when Morse code was first invented, that we called when someone's sending their uniqueness of sending their fist, and that goes back over 100 years. So people who are sending all the time have very specific styles of sending. They have a very unique fist. And people who are doing this all the time, who are contacting the same kind of people all the time because they're buddies, so to speak, they can listen to the Morse code being sent and they go, oh, that's Henry or that's Julie, because they recognize how they send Morse code. It's sort of like, for lack of a better term, it's everyone's individual accent, and they can recognize that. On the receiver elements, we have a couple of key things to keep in mind. We have sensitivity, which is the ability to detect signals, and also referred to as a minimal detectable signal, and it's usually measured in microvolts. And sensitivity is basically saying how weak a signal can I actually amplify and extract the information from and make it known. The preamp is a amplifier that can boost the sensitivity, allows you basically amplify a weak signal that's barely heard and may not even be hearable, and boost it up enough that we can now process it. However, remember, when we boost a signal, we also boost the noise. And then we have what's called selectivity, which is the ability to discriminate between signals. And so if you have a signal that is only 3,000 hertz wide, but your receiving radio has a selectivity that's 4,000 wide, and you have two transmitting stations, one is going from, let's say, 0 to 3, I'll say that's 14 point, let me just stop. Let's just say one is at 0 to 3,000 and the other signals from 3001 to 6,000. And if we had a receiver that had a bandwidth for selectivity of 4,000, it would be possible for us to not only hear the station that's going from 0 to 3,000, but we'd also hear part of the station that's going from 3001 to 6,000. And therefore we would hear distortion because we'd hear two different transmitting stations overlapping on each other. So selectivity is a way of us to discriminate between signals. And even though on SSB, for example, the traditional bandwidth that we use for radios is about 2,800 hertz, you have a choice in most modern radios to have filters put in especially when the bands become very crowded and people are talking literally over each other, not on purpose, but because sometimes one station is not in the range of the other station, but it's in range of you, so you could hear both stations. You can actually, in some radios, change that 2.8 kilohertz bandwidth to, let's say, 2 or 1.8 kilohertz bandwidth, which means you may have lost some of the voice reproduction, but you've also narrowed down other stations that may be overlapping it from being heard. So that's what selectivity is about. It's basically being able to discriminate between signals. And as you just heard me mention, we can use filters to change that selectivity a little bit so that it makes it easier for us to hear stations that may be overlapping a little bit with each other. And for SSB, as I said, you can go from 2.8 kilohertz to 1.8 kilohertz. And for CW, you can go usually to 500 hertz and lower for CW in changing the bandwidth if there's overlapping stations. So let's talk about the rules of the road. We've had a lot of technical information. Now let's get into some of the rules of the road. So here's some just basic standards of communication practice. One, you have to understand the federal operating rules under Part 97. You need to know and follow the volunteer band plan for your region and country. And this is really important. Band plans are volunteer basis. There are band allocations that are part of the federal operating rules. That's governmental law regulations, Part 97. And then how we divide up those bands is the voluntary band plan. And we want to follow that band. We want everyone to follow that band. Are you obligated? Are you going to get fined if you don't? No. But we encourage everyone to do that. Be respectful and open to sharing the bands. Avoiding intentional and unintentional interference is extremely important. And repeater operations, understanding how they work. How to make a contact or break into a conversation using correct etiquette. And of course, there's a special etiquette for operating in nets, and that is when you have a group of people operating together. You need to understand the different operating modes, FM, SSB, for example, and digital modes. And what are the things that are specific about public service communications? And yes, we are a hobby. We are an amateur radio group of hobbyists, but by law, we are actually not called hobbyists. We're called the Amateur Radio Service because it's recognized that we provide a service, especially in times of disasters, emergencies. Because of that, you have certain rights in that emergency that you may not have normally. Well, let me put it this way. There are certain rights you have today that exist because of you being a federally granted service. For example, if you operate, I encourage you not to do this, but if you were to operate your FM radio while you're driving, in I think almost every state so far, you cannot be fined for distracted driving as if it was a cell phone because you're considered part of an emergency communication system. So you can talk on your radio if you're driving, although I highly recommend not doing that. However, always carry your license in your wallet. Don't argue with the police officer. Take the ticket, just go to court and bring your license. And also have the officer document on the ticket that you showed them your radio license so it's well known that you were legally able to operate. But I do recommend pull over. Okay, we went over this as the technician license allocations. Please know this. There's always going to be at least a couple questions on the test about this table. So be very, very aware of it. And that you have a 200 watt allocation limitation in the HF bands. So let's look at this is a typical generalized view of the bands that were allocated. The U.S. amateur radio bands, and look at the top, U.S. amateur power limits, what it says. It's an FCC Part 97 statement. It's a little blurry, but I'll tell it to you. You must use the minimum power necessary to carry out communications. This means that if you made contact at 100 watts, let's say, then the person said, you are booming. You're loud and clear. You're like blowing my meter off, so to speak. If you're really coming in, you should automatically then say, I'm going to reduce my power to 50 watts. Can you still hear me okay? Yep. Okay, let's try 30 watts. Okay, you still hear me? Yeah, that's fine. Okay, let's do 30 watts. So technically, you want to use the minimum power necessary to carry out communications. Why? Why do you want to do that? Well, if you're talking to Johnny, 800 miles away, and you're booming at them with 100 watts or more, that means that not only is Johnny hearing you, but there are other stations that may be wanting to use that part of the spectrum who are 1,000 miles away, who you are now using that spectrum. And by reducing your power, you may have a conversation with Johnny, and now you're only going 800 miles in distance, but the people who are further than 800 miles can use that same frequency and would not be interfering with you, and you would not be interfering with them. So that's the whole idea of reducing your power to where it's needed. I'll be honest with you, that practice isn't always used, but it is a good thing to get in mind. So your allocations, this is exactly from the table you saw on the previous slide. In yellow, here's your allocations. You can see it's CW only, but it really means CW and data are allowed in those locations that you can use. You'll notice it has EAGNT on these charts. E is extra class, A is advanced class, G is general class, N is novice class, and T is technician. We only have currently 3 levels of licenses: extra, general, and technician. However, we used to have more levels of license, and they have been grandfathered in, And so you have the amateur advanced license. There are people who still have that. Generally speaking, they have an A designator in their license, so they'd be A7JT, for example, and they have the same allocations as an extra, and because they've been grandfathered in, because that license is, you can't even get it, there's no test for that anymore. However, you hold that license, you just keep renewing it, and it's fine. If you had a novice license, which oftentimes was only good for 1 year, but you were at the changeover period when we went from the novice license being a real license, a legal license, to no longer, then if you were holding it, instead of it automatically expiring, you could leave it there for a lifetime if you want, or as long as you renewed it forever. But you would be limited to only the things where the N is showing. Uh, so there aren't a lot of N's left. There are still a number of A's left. Uh, and so slowly but surely only E, G's, and T's will be around. The greatest population of amateur radio operators are technicians. They make up the bulk of all the amateur radio operators. So you see where your allocations, they match the table previously. You can see on the 10-meter band, you have SSB phone as well as RTTY and data. RTTY is radio teletype, and we do that now in software, not with the old teletype machines. But if you look from 6 meters and higher, everyone's allocation, except for novice, who really doesn't exist anymore, everyone's allocation is exactly the same. You have, from 6 meters and above, you have the same allocation as everyone else does. So you have free to ride anywhere you want there. So, and then remember, a band plan is voluntary, and then we have detailed band plans, and these are all available online through the arrl.org site. And here's a 2-meter band plan for 144 to 148 megahertz. And you can see we have Earth, Moon, Earth, Earth, Moon, Earth for Morse code at 144.0 to 144.05. And that is the idea of having a set of antennas to bounce a signal off the Earth, or bounce a signal off the moon and back to Earth. And so it's basically another form of satellite, so to speak. So I aim my antennas, they're special directional antennas, at the moon, and somebody is aiming their receiving antenna at the moon, and I can transmit to them, and hopefully they can hear it, and vice versa. And then we have areas for like SSB calling frequency. So if you want to do weak signal, single sideband calling in the upper sideband on 2 meters, you can do that. That's where the all mode transceivers come in. Then you would call 144.200 would be your calling frequency, which means I would call for a station to want to talk to me at that frequency. And then once we said, hey, when someone came back to me and said, yeah, I'd like to talk to you, then I'd say, okay, let's move our frequency to 144.210, for example, and we'd move there. Why? Because we want to free the calling frequency up for others to make contacts. And when I finish with that contact, I might drop back to the calling frequency to call out for somebody else. Then we have places for beacons. We have Oscar subbands, and Oscar subbands are our satellite system, the orbiting satellites that are designed and operating for the amateur radio frequencies. There's the uplinks and downlinks and translators for those satellites. We have places for the repeaters. For experimental modes, we have frequencies that are allocated for experimental codes. And again, if you were doing something like simplex in the experimental area, no one's going to yell at you. It's just the fact that these are suggestions. And then we have 146.52 is a national simplex calling frequency for FM. So for example, if I'm in my car and I'm driving on a long trip, I might switch my dual band mobile radio from local repeaters in the Seattle area to 146.52, or at least one of those, to 146.52. And when I'm driving, I might call out to somebody, call out, is anyone listening while I'm driving, and have a conversation with them, or somebody might be calling on that frequency and I'll have a conversation with them, or somebody might be calling on saying, I have a flat tire, I could use some help, can you call me I'm out of cell range, are you in cell range, can you call a tow truck for me, or whatever. So that's our general, calling frequencies for FM. So you want to be able to understand this and stay within those areas if you can, so that you're not interfering with anybody else's work, but you're also being able to get hold of people who you want to talk to in those modes. On the right, you see a porcupine vehicle, for lack of a better term. And this van is carrying 3 complete 10-band antenna systems, 12 transceivers, 15 microwave transverters, and an assortment of amplifiers. And this is a rover station for VHF and UHF and above. And this station is somebody who is driving out to sites where there is no amateur radio operator operating in these frequencies, and during a contest, they are opening up that section for other amateur radio operators to be able to call that location, because there are points for getting, let's say, every county in a state or a region, in certain regional areas, in part of a contest. And then these will move on to a different location, and they'll make contacts with people across many different frequencies. So a lot of these setups are removable once the contest is over. They can slip them off their trucks, and then when there's another contest coming, they put them on again. And so people do this as part of as getting points, and also as a service to other amateurs. And yes, as I mentioned, where we have allocations in the around the 2.4 and 5 gigahertz allocations, and we do have amateur radio operators who set up mesh networks and wide area networks, and you can learn more about them by searching on the Arden Mesh Network or HamNet or HamWAN or other or mesh networks, searching under Ham Mesh Networking, and you'll see that there are networks around the city in different capacities, and they will have one node at least that's attached to the internet. So yes, you are able to surf the internet using amateur radio frequencies and essentially being off Comcast for all intents and purposes. But every mesh has certain rules, and every WAN that an amateur radio group operates has certain rules, so you have to make sure you follow their rules. And of course, you cannot carry on any business when you're using the internet, so you can't run your business through the internet using the amateur radio frequencies. We do have some special rules because we have neighbors, and so the number one thing, and this is for across the board for any band you're in where we have rules regarding interference and secondary allocations. If you learn that you're interfering with a radio service outside the U.S. or somebody who's had primary allocation into a band, like in 60 meters, you must stop transmitting. So for 60 and 30 meter band, as I said, we're secondary allocations. We must avoid interference with primary users. As a technician, you do not have allocations in the 60 or 30 meter band. However, the ANC lines, you have allocations in those bands because these are primarily around the UHF area, or UHF bands, and we have the A line, which is 50 miles or so south of the U.S.-Canadian border, and the C line in Alaska is similar. And these are about having frequency coordination below 470 megahertz in the UHF band with Canada. And so it's possible that you might have a situation where you cannot use a certain frequency pair in the United States if you're within the A-line area because you're interfering with somebody in Canada's repeater, for example. So they would be a frequency coordination to make sure that that doesn't happen. There's also one special area. You have no privileges in the 630 meter band, but we are limited to 1 watt near Russia from Alaska when we're in that band allocation. Not a lot of people are operating in that area, but just so you know, it's the only thing you really have to be responsible for the test is the A and C lines. And then you have to also remember what ITU region you're operating in, because that defines what your band plan is. So if you're in a licensed amateur in the United States and you are going to operate in another country, you need to know what ITU rules are in that country for band allocations, because even though you may have a band allocation in the United States for a certain part of the band, in another region you may not. And so you are bound by whatever that region's allocations are, regardless of what your license is. We also have some definitions. A beacon is a network of amateur radio operators running automated transmission and receiving systems we use to determine current propagation conditions, and for example, the Weak Signal Propagation Report Network, or WSPRnet. And we have weak signal modes, which are again for 50 megahertz and above is CW, SSB, and digital. These that's what we define as weak signal in context to your technician license, as I said before. I've also mentioned we have satellite uplink and downlink frequencies, and there's segments of the bands where satellite communication occurs. An uplink is you transmitting to the satellite, and a downlink is the satellite transmitting to you. So if you're transmitting to the satellite, and it's going to downlink at a different frequency, which the other person on the other end of the Earth who you're talking to will be listening for. And then when that person transmits to you, they will transmit to the uplink frequency, and you will be listening on the downlink frequency for their transmission. Simplex is transmitting and receiving on the same frequency, so we take turns. You might actually hear us say, this is, hey, things have been pretty good. I'm feeling pretty good. What do you think? Over. guess what? We still say over from time to time so that somebody on simplex knows that we're done talking. And then sort of like satellites, we have repeater inputs and outputs. Similar to satellites, like I said, there's transmission on one frequency to the repeater, and the repeater transmits what it receives on another frequency, and that's where you receive it. So where the transmitter, where we'll get into this, where the repeater retransmits is where you're listening, and this is called half duplex. Now you also have to be familiar with certain other terms like the control operator. The control operator makes sure all FCC rules are followed. One station, one control operator at a time. The station licensee designates the control operator. So if I own the radio station, if I own my shack, for example, and so if you come into my shack and you have a license, I can say to you, okay, you're the control operator. And I can literally leave at that point. And you can then go ahead and operate the station, but you're now in charge of following all the rules and making sure anybody else who's there is following all the rules. And the control point is where the control occurs, and it can be remote. So you can operate your station from another location. So repeaters are really remote operated stations. I can operate my HF station by having through the internet, where I have a computer simulating the front of my radio, but my radio may be located hundreds or thousands of miles away, and I'm connecting to it through the internet and operating a transmitter with an antenna at a different location. But I'm the control point here in my shack, which might be not where the radio actually exists. And then an unlicensed person may operate a station under supervision of a control operator. So when I teach a class at the Red Cross, oftentimes during lunch, I will invite people to come down to the radio room, and while I'm having lunch or they're having lunch, I will supervise them getting on the air and making contacts. So a guest must use the call sign as a station licensee if the operation is within the owner's privileges. So the guest must use the same call sign as the station licensee if the operation is within the owner's privileges. So if you and I have the same license and you come over to my shack, then you will use my call sign. Guests with a higher class license will use both call signs if they are operating in a band where the station licensee does not have privileges. So if you're a general and I come to class licensee, and you come and I come to your shack and I'm an extra licensee, and if I want to operate in an allocation that you do not have as a general, then I would use your call sign and my call sign, which indicates to people I am not operating my station, I'm operating your station, but I have a higher license grade than the person who owns the station has. Whew, that's a mouthful. So let's go into what a repeater is. And basically it's very simple. A repeater is a way to extend the coverage range of a given VHF or UHF radio. Remember, in VHF and UHF, mostly it's line or higher, it's mostly line of sight. So a radio that's placed as a high point as possible means it has line of sight with many, many people across a wider range. Again, anyone with line of sight and sufficient power can then use that repeater to talk, listen through it. And users' radio automatically will switch between the transmit and receiver frequency. So that's one of the things. You don't have to do it manually. It's all pre-programmed in. When you set up the repeater for your radio, you're programming a whole bunch of parameters in. Those parameters then will, when you hit the push to talk button, will change the radio's frequency from the receive frequency to transmit radio frequency. When you let go of the push to talk button, it will then return back to the receive frequency. So here's an illustration of a repeater setup. Here we have a repeater on a water tower, and this is a real repeater somewhere in, I think it's in Texas or somewhere, and it basically has they probably have a very flat geography, so the water tower is relatively easy to see by everyone. So on the red, we see the user is transmitting in this example on the repeater's listening frequency, 447.100 megahertz. The repeater is going to be listening at 447.100 megahertz. So, and then it's going to retransmit at 442.100. And the person on the other end in blue, or purple if you want to call it purple, is going to be listening at 442.100. So look at the pattern here. The person is transmitting at the frequency the repeater is listening at, and the person who is going to be talking to you is listening to the repeater on the repeater's frequency it's transmitting at. So that's the pair. The repeater is listening at 447.100, therefore I have to transmit at 447.100. And if I want to listen to what's being retransmitted by the repeater, I have to listen at 442.100. And so that's the idea of how these pairs work. I transmit at the same frequency that the repeater is listening at, and I listen at the same frequency the transmitter is, or the repeater is transmitting at. And that's what's happening with the repeaters. And so as long as we all have line of sight, we can all hear the repeater. Now, one of the things that you'll see in this sequence is there was a special thing called the CTCSS tone in the small diagram. We're going to go into that right now. And it's a set of radio, and all these radios use what's called the PL or private line subaudible tone that limit what they can hear on a given frequency or pair of repeater frequencies. This was developed by the Motorola company many, many years ago, decades ago, because in business band, oftentimes there was not enough frequency to go around for all the businesses, so oftentimes businesses would share frequencies. So you might have a tow truck company sharing the frequency with, let's say, an ambulance company, or two ambulance companies that are separated by 20 or 30 miles sharing the same frequency, and it's possible that sometimes they will get in a situation where they could talk to each other inadvertently, interfere with each other's communications inadvertently. So what they had was this what's called a private line tone. So when someone pushed their push to talk button to start transmitting, a subaudible tone would be transmitted out. The radio that was tuned to that tone, that was listening for that tone, would turn on, so to speak, and you can then transmit through it and receive from it. If you didn't have the right tone, that radio would not retransmit. So that way, if the tow truck company was talking to their people on their transmitter and receiver, I couldn't hear them if I was working for the ambulance company on the same frequency, and vice versa. Is it possible for me to hear all the traffic? Absolutely, because you can turn the receiver in such a way that it doesn't need a private line tone. In other words, you can turn off the private line tone for receive, so you hear the entire band at one time. If I keep it on, then I only hear what's designated for me, and I only transmit to who I want to designate to. So one of the things that we use is what's called a squelch, and a squelch is the process of setting the radio to mute the speaker until a signal is above the noise floor or has provided the right PL tone or code. So normally when we have a radio, and if you turn on a radio, you hear a lot of white noise on the receiver. It's very exhausting to hear that white noise. And mostly in FM repeater work, we don't want to hear that white noise at all. So we turn the squelch up until we no longer hear that white noise. Now any signal that's higher than the white noise will then turn off the squelch and turn on the speaker, and I will hear that signal. And when the signal goes away, the squelch will then turn back on and I won't hear any white noise. And a PL tone is designed to override that, so that even if a signal is higher than the noise floor, the squelch will not turn off unless it has the right PL tone. If it has the right PL tone, it will then turn the squelch will turn off. I'll hear that call that's designated for me. When that call goes away, the tone goes away, the squelch turns on, I won't hear anything anymore. And so that's why squelch works in two ways. One way is that it mutes the noise floor until a signal comes above the noise floor, or it will mute the noise. It will mute the noise and the signal until the right PL tone comes in. CTCSS, continuous tone coded squelch system, is an analog PL tone. It's very similar to the PL tones in general, subaudible. And it's a code that's used and transmitted such that it will then activate everybody who's in my group, so to speak, or that repeater, and all those who can listen to that repeater. DCS is digitally coded squelch. It's a digital version of the PL tone, acts very much like CTCSS. And then oftentimes you might hear on a repeater courtesy tone, and it's optionally used at the end of a repeater transmission to signify the operator is finished and can be used instead of over. So if I'm talking on the repeater and I said, okay, well, that's about all I have to say, over, or I can just say that's all I have to say and stop talking. When I stop talking, the repeater will recognize I stopped talking. It'll set out a beep, and then the repeater will call drop, which means it's going to then be ready to take on anybody else wanting to talk through it. So let's look at this example. We have an antenna. We have two operators with two radios. Operator A has a transmit frequency of 146.82 megahertz. They're putting out a CTCSS tone of 103.5. We have operator B radio who's putting out the same transmit frequency, but their CTCSS tone is 85.5. They're both coming into the antenna. If the receiving antenna hears 103.5, it will then activate and say that radio operator I want to listen to. The other one I don't want to hear at all. So when it hears that 103.55, it basically activates, and when it activates, that is the both CTCSS match, then the control system activates the transmitter. The audio is sent from the receiver to the transmitter, and the transmitter sends out the message with a 103.5 tone, which means the operator A, when they're in the receive mode and their tones match, their radio will basically turn on the speaker, and you will then hear what the repeater has to say. And so that's what the CTSS and DCS tones and PL tones are doing. It's telling the receiver when to listen and when to ignore. And then if it's listening, it knows to send the audio over to the transmitter to retransmit at a different frequency. But with another, and you can have two different, you can have a PL tone for receiving and a PL tone for transmitting. However, the general rule of thumb is that they both are set to match in the amateur radio systems. And a few more things about working with repeaters. They can be an open or closed system, and repeaters can be open, that is, they publish what the CTCSS or DCS code is, or not publish, which means it's limited to only certain members can use it. This doesn't always work anymore because many of the modern radios today will scan for the subtones, tell you what they are so that you can actually use those repeaters. But most amateur radio operators don't want to use a closed repeater, so you'll very rarely find a closed repeater. Repeaters often have timeouts of 2 or 3 minutes where they will drop in case there's a stuck microphone, also to keep people's conversations shorter. So after 2 or 3 minutes, the repeater will drop the conversation. You can rekey your mic and start again if you want, and that's often what people do, but they'll often recognize what happened and they'll say, oh, sorry, I dropped the repeater. I'll just finish up with this 1 or 2 things I want to say real quickly, and I'll open the conversation up for somebody else. Now, part of the repeater is what's called a duplexer. So you see the controller on the right controlling the transmitter and the receiver. We see the input to the receiver, that is from the antenna, and the output from the transmitter to the antenna is going through a duplexer. And the duplexer enables one antenna to serve receiving and transmitting simultaneously. And it can do this because it has a special device called a cavity duplexer, which is a very expensive and very sensitive filtering system that allows the receiving system to only hear the receiving frequency and the transmitter system to only send energy to the antenna. So if the transmitter got energy into the receiver would be not only damaged, but if it didn't get damaged, it would be locked into the transmitter frequency and it would not receive during that time. So this type of special cavity duplexer is designed to allow one antenna to be used for both transmitting and receiving. It's a very sensitive piece of filter equipment that only allows a very tight area for the receiver to pass and only allows one tight area with the transmitter to pass to the antenna. And it's also possible to link repeaters that you can share the receiving and transmitting signals across a set of repeaters to extend their range even further using either direct lines, not used too much anymore, or using the internet, which is used quite often now. So literally you can have a repeater in Seattle tied to a repeater in Snoqualmie, tied to a repeater in Yakima, tied to a repeater in Spokane, tied to a repeater in Idaho, into Montana, and you can talk on one and talk all the way across these states to somebody on the other side. Now, when you have a repeater capable radio, you have to be able to program it with all the different things, which is the frequency pair, the offset, and the PL tone. So you can do this manually or you can use software. However, I highly recommend you always know how to do it manually because there are times when you need to switch to a different repeater or change something during a certain situation. You may not have a computer around to do the programming with a computer, so therefore you need to know how to do it manually. So it's also why I keep my booklets for my radios near my radios so that even when I'm in the car, if I need to reprogram and I can't remember how to do it, I can just really reach for the book. Whether the book is on your phone or the book is a piece of paper, always know how to, and do practice, always know how to reprogram your radios manually for new repeaters. But you can do this oftentimes with software. There is one software that's open source that's being worked for almost every radio these days, popular radio, and that's Chirp. And you can then download Chirp, attach it to your radio, and then you can use it to program your radio in mass through a spreadsheet. And then you can save different configurations for the radio, different setups, so that, let's say you do a lot of camping on and operating over on Ocean Shores area, like 2 or 3 times a year. You might be out there for a couple weeks, so you may have a configuration with all the repeaters in that area, but you don't need them when you're in the Seattle area, so you have a different configuration for the Seattle area, and you can change it on the fly with the software from the programming very quickly. And then again, you're going to program the frequency pair, the offset or shift, and the PL tone. So remember, we have 2 pairs of frequencies for repeater. One is the transmit frequency, your transmit frequency to the repeater, and your receiving frequency from the repeater. That's the frequency pair. The distance between those frequencies is called the offset or shift. On the right, you see the common offsets for those different bands. Many times, almost every modern radio today, you can program it to say automatic shift, because it's already known what these shifts are going to be. And so therefore the radios, if you enter in your transmit frequency, it will automatically shift for the receive frequency and vice versa. But you will have to add what PL tone you want to use. And if it's using CTSS or DCS tones, you'll have to look it up or find it in some way. There are repeater books out there. There are repeater books online. The repeater books you can buy. For this area, I recommend going to mikeandkey.org, and you'll find a list of all the repeaters in this area, their offsets, frequencies, as well as nets. When you're making a call to a repeater, you're calling out for any station to respond. So you're just driving around, let's say, or you're sitting somewhere and you want to see if anybody's out, you want to have a conversation, then you can just call out, "This is W7DAO monitoring." You can also say, "This is W7DAO listening," and that's an indication that, hey, I'll talk to anybody who's out there. You might hear someone come back, "W7DAO, this is K7RBW." Oh, okay. I'd say, "K7RBW, hi, this is David. How's it going?" We start a conversation. And maybe somebody didn't answer. Okay, so maybe every 5 minutes I might call out, or I may call out a couple times and stop and not call out again. Nobody's around right now. If there's a conversation already going on, a social conversation already going on, wait for a break in the conversation, and all you have to do is say you can say one of 2 things. You can say W7DAO, or you can say break. I prefer myself W7DAO, but others will say break, and then you'll wait, because if they heard you, somebody will come back and say, "Go ahead break," or "Go ahead W7DAO." When they acknowledge you, then you give your call sign, "Hi, this is W7DAO, and I just wanted to add a comment to the conversation, or see if I can join in," or whatever request you want to make to them. If you're calling for a specific station, then you would call it out as, "Hey, their station first, then mine. K7RBW, this is W7DAO." I would wait. I might repeat it 2 or 3 times. If there's no response, I would clear that frequency by saying W7DAO clear. If they were to respond, I'd say K7RBW, this is W7DAO, and just like before, they'd say W7DAO, this is K7RBW. I'd say, "Oh, hi Bob, how you doing? I thought you'd be on the air. You have a few minutes to talk. We just have a conversation." Now, emergency traffic is a special situation, and this goes for any band you're on. If no one is talking on the repeater and you have emergency traffic, first, ideally find a repeater with a conversation already going on. Otherwise, you're going to have to call on any repeater. Also check 146.52 if you're on a FM radio, which is the simplex calling frequency, and don't be afraid to call on that frequency either. If there's nobody around, try any frequency you can find that's in your legal allocation. So you would then find a repeater you want to be on, say, "This is W7DAO, I have emergency traffic, is anyone there?" That's if no one's talking on the repeater, you just go, "This is W7DAO, I have emergency traffic, is anyone in the air?" You can wait a minute or 2 and then repeat as needed. If there's no response after a certain period of time and you want to move to some other repeater to try, just say W7DAO clear. Or if you want to just stay on the channel but you're going to listen in case somebody does come back to you for a few minutes, then say W7DAO monitoring. So monitoring also means listening, right? That's what we talked about before. If a conversation is also already going on a repeater, which is the ideal situation, if you have emergency traffic, you want to find a conversation that's already in progress, wait for a break in conversation. You can call out break, break. However, I guarantee you, some people may forget that this means emergency, so use break for emergency traffic. So I always recommend, although break is one of the official things, I always recommend be descriptive, break for emergency traffic. Wait until they acknowledge you, and then state the situation and what you need. If you're making a simplex call, that is HF or without a repeater, there's simplex frequencies on VHF and UHF, of course. Calling out's a little bit different. You're going to use what's the old-fashioned traditional way of doing it, which is you're going to calling out for a station to respond, which is CQ. CQ is anyone out there, anyone out there. This is it. It does not mean seek someone, seek you. If you want to go for Wikipedia, you'll find what CQ and CQD's origins are. But today it means, is there any station out there who would like to talk to me, essentially? So you'd say CQ, CQ, CQ. This is W7DAO, Whiskey 7 Delta Alpha Oscar. CQ, CQ, CQ. This is W7DAO, Whiskey 7 Delta Alpha Oscar. CQ, CQ, CQ. This is W7DAO, Whiskey 7 Delta Alpha Oscar. You can repeat the sentence 2 or 4 times as you desire. Wait 15 to 20 seconds. Repeat the process again, and continue the call. Wait and repeat patterns as long as you wish. When no one's there anymore, if no one's responding, just after you get tired, say W7DAO is clear. If someone does come back, then confirm their call sign and start a conversation. When you finish with this person and you want to talk to another station, you have some choices. You can say W7DAO QRZ or QRZ, and QRZ means ready for the next call. And if there's another station there, would you like to talk to me? And if there's no answer, then you can start the CQ process again, or if you're just done, say W7 is clear. Why you say clear? To tell people that you're freeing up the frequency for someone else to use. What if you want to do emergency traffic? Same thing you heard before. Same thing exactly that you heard before on VHF or UHF FM is the same thing for running simplex. We also have ways of reporting signal because everybody wants to know, how's my signal getting out? It's the equivalent of, do you hear me now? Or can you hear me now? So it's common on HF and weak signal work. I will tell you the RST process, signal reporting system, is badly used. It's often abused during contests when everyone suddenly becomes 5'9", because it's quick and easy to do. It doesn't take a lot of thought to give everybody the same number. But ideally, you want to give people the readability and strength report. You only use tone for CW or for digital in some cases. And so oftentimes, you can see that the R goes from 1 to 5. Unreadable, barely readable, occasional words distinguishable, readable with considerable difficulty, readable with practically no difficulty, perfectly readable, and then signal strength. So when people keep saying 5'9", 5'9", 5'9", they're saying you're perfectly readable and fairly good signals. Or excuse me, perfectly readable and extremely strong signals. Well, when I get a 5'9" with 20 watts and I'm talking to somebody in New Jersey, I know I'm not an extremely strong signal, but they're just being lazy. So it would be nice if people were a little bit more diligent about using the process consistently. And I have other people I talk to who are not in contests. Well, they'll tell me what you're 3'3", you're 4'4", you're 5'8", things like that. So, but generally for contests, oftentimes they're not giving you accurate reports. Other signal reporting systems are you may hear the old school 5x5, which is signal strength and readability. So strength comes first. You're fairly good signal, and your readability is good, so you'd be a 3-4. So that's one system. Again, these are all subjective systems, so just be aware of that. There's also what's called, fairly new, the circuit merit system, mostly used in FM right now, and they go from Charlie Mike 5 to Charlie Mike 0. And Charlie Mike 5 would be no noise, full quieting. When full quieting in FM means that you hear no scratchiness, it's broadcast quality. So most people are Charlie Mike 4 and 5 on a repeater. And just so you know, what you're really rating on a repeater is the audio quality, not the signal strength, because essentially with the repeater, everybody gets the same signal strength because they're listening to the repeater. What you're really giving them is the audio quality coming into the repeater from their transmitting unit, because that's the part that's variable. Oh, you got a slight hum in your signal. Okay, well that's not from the repeater, that's from your side, because the repeater signal strength will always be the same because it's the repeater. Versus if you're running simplex, the signal strength will vary based on what station's listening to. We have Q codes, and they're holdovers from Morse code are still used in Morse code. There are lots of Q codes. Really, we only really use a handful of them at any given time. Uh, the interesting thing about Q codes is they're questions and statements simultaneously. They change with context. So if I'm saying to somebody, uh, for example, let's say I'm giving my call sign for something. I say W7DAO, and the person says uh, W7 Delta Oscar. I say no, Whiskey 7 Delta Alpha Oscar, and they'll say Whiskey 7 Delta something Oscar, and I'll say Whiskey 7 Delta Alpha Oscar QSL. You hear my voice go up. It's a question, and the person says, "Oh, Whiskey 7 Delta Alpha Oscar QSL," which I just said is, "Did you get that?" And they came back and said, "Oh, yeah, I got it now. Thanks." And so a Q code can be a question and an answer simultaneously. And so on the right, you'll see, so if I say QTH, person might say, "Oh, I'm in, Texarkana." And if I'm talking to somebody and I say, "By the way, my QTH is Seattle," that's a statement. So again, these are statements and questions simultaneously, depending on the context. Now, a little trivia. Before there was LOL, laugh out loud, amateur radio solved that problem 100 and some odd years ago because we say hi hi. It doesn't make sense to click the radio, push to talk, and start laughing on the radio to indicate that something's funny. So you'll often hear amateur radio operators say hi hi, which means they're laughing. It's the equivalent of LOL, and it's been around for 100 years. And it was sent for Morse code. So if you look at the Morse code, dit 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 dit. So it was very quick to send hi hi. And so that's where the origin of our laugh out loud came from. We also have phonetics, standard international phonetics. We want people to use standard phonetic alphabet, especially when you're doing any type of net control, any type of thing like that. You want social net or tactical net or emergency net. You want to use standard phonetic alphabet when you're doing contests because that's what the person who's on the other end's mind is thinking about. It takes less time to process if you use standard phonetics. So when I say Whiskey Alpha Delta 7, whatever, your brain is tuned after a while to listen to hear that, versus wild wild alligators. Your brain doesn't. It takes a little bit longer to figure out what the heck are they doing. And people saying instead of saying Romeo Oscar Juliet or Romeo Oscar Golf, they'll say running out of gas. Well, it takes you a second longer or two to figure out is that their call sign? Unless you know them and you've talked to them a lot of times. So it's very good. Very best practice is to always use your standard phonetics when using call sign. Also your name. So people say, "Hey, the name here is David, Delta Alpha Victor India Delta." And why? Because sometimes with some people's accents, it's very difficult to hear some of the things they're saying to translate them. And so by using standard phonetics, it's easier to figure out that that person with that very strong Japanese accent is saying their name is this, or they're hearing me with my strong American accent saying something that they can decipher because we're using standard phonetic alphabet. The other thing is pausing for a station identification. I forgot why I put start again here. But each amateur station except the space station or telecommand station must transmit its assigned call sign and its transmitting channel at the end of each communication and at least every 10 minutes during communication. Doesn't mean that if you're having a normal conversation, you don't have to say your call sign every time you finish saying a sentence. It just means that once you get into the conversation, you don't have to say your call sign every 10 minutes. The other thing is you cannot do an unidentified transmission and what's called kerchunking on FM repeaters. Sometimes people want to test if their radio is kicking the repeater over because all they need is an RF carrier to do that. They'll hit the PTT, they'll hit the push to talk, they won't say anything and then they'll let go of the push to talk and they'll hear the repeater respond in some way that tells them that they were able to get to the repeater. That's an illegal transmission because you didn't identify yourself. So you don't do that. What you do, if you want to test the radio in some way like that, you then say W7DAO testing. If you only need, and also when you're going to do your every 10-minute identification, you don't need to say W7DAO for ID. There are people who do that. It's not necessary. If I say, hey, I'm doing fine, I'm going out to do some errands today, W7DAO. That's it. I just have to put in my call sign. It doesn't even have to be part of the conversation. I don't have to say for ID, because if you're using a call sign, it means you're doing it for ID. You must communicate your call sign in English. It could be communicated in Morse code, in an image if it's slow scan TV or amateur TV. It can also be part of a digital transmission. It has to be. And you can use self-assigned indicators. So you could do things like, hey, I'm W7DAO/W1 for whatever W1 is supposed to mean. It could be part of a tactical call sign. But I could say W7DAO/6. What does that mean? It means I'm W7DAO, which means I'm operating from usually Washington or the 7th sector or Oregon. But right now, today, I'm in California. So I want you to know that even though I have a W7 call sign, I'm operating from California. So it says W7DAO/6 indicates to people that I'm actually in California. So we're going to stop here for now, and we'll pick up later because I want to go into a lot more detail on actually what net control is like, tactical nets, social nets, emergency nets are like. So we're going to stop here for now, and we'll pick up again at the next session. And again, as always, if you have questions, please email me, and we'll take it from there. See you next time.